next speaker is João Sato from Federal University of ABC region in Brazil. And he will tell us more about everyday neuroscience and functional near-infrared spectroscopy.
Well, good afternoon. I'm really grateful for the honor of being here. It's really a pleasure. Thank you for the organizers for your kind invitation. Professor Boas, thank you so much. So my name is João Sato, and I am from Brazil. Yes, I have this Japanese face, but I was born in Brazil, and this is why I have this funny accent. And I'm third generation from Japanese immigrant families, and I don't speak a word in Japanese. Well, I came from this hot spot, very from the south, and these are some pictures from São Paulo city, where I live, and these two bottom pictures are from the university in the region of ABC, in the neighborhood of São Paulo. It is an industrial region in Brazil. And just to provide some context, I started my research career 20 years ago investigating the neural correlates of psychiatric disorders using MRI. This research led me to study neurodevelopmental trajectories and the interfaces between neuroscience and education. And well, I had two kids, and somehow my life changed to these kids, and so now I love children. I even did a bachelor in education as well, and this is why I love kids so much. And it was during the studies with children and applied neuroscience that I got interested on functional near-infrared spectroscopy, in which our chair is a world star, Professor Boas. And so in my presentation, I will show some studies depicting some possible interfaces between applied neuroscience, the learning science, education, and the role of FNIRS in this field. Okay, I think I don't need to speak more about the basics of FNIRS, I think, for today. Okay, so I will start by posing this question. Why and when should we use FNIRS? The first time I heard about FNIRS was in 2007, and at that time, I was intensively working with fMRI. Well, it happens that everyone knows that fMRI has a greater spatial resolution. So at that time, I honestly did not see any reason to use FNIRS but the relative low cost. And of course, for Brazil, a developing country, this could really make a difference. But at that time, I was already working with fMRI. And now I see I was really short-sighted. When I started working with applied neuroscience and with kids, a new question raised. What could we do with FNIRS that would be impossible or very hard with fMRI because of its constraints? So from that point, my view, my perspective on FNIRS changed completely. And obviously, FNIRS has many specificities and limitations, but I decided to explore, test, and know more about it. So this question led us to many tests and experiments starting in 2015. And some of these experiments were presented in this paper. And, well, it is important to mention that the main aim of this study was not to answer any question about the brain functioning, But to demonstrate that even without too much signal processing methods, like fMRI, we could still see some promising features in the signal. So in other words, well, here we are in a data science building, if I'm not wrong. And if you need to torture the data to see what should be obvious, perhaps you are just, fishing the methods to get the results you want. And in FNIRS, I was really impressed, and I will show why. Oops, okay. So in this study, we presented some illustrative experiments to check signal quality and the potential findings, such as, well, I have this Japanese face. I play table tennis. And so I did, my trainer was a volunteer. My coach was a volunteer in this experiment. So some experiments just like in table tennis playing, piano playing, and violin dual hyperscanning. So, and we observed 2 points. First, the signal quality was affected by the level of motion required to perform these tasks. For example, a forehand ball in table tennis requires more movement than rest, and a two-sided ball requires more movement than only one side. And we can see that the signal quality is different here in this situation, but the movement artifacts are not so huge. They seem to be handled. And second, we had an increased prefrontal activation in more complex conditions. For example, the predictable versus unpredictable sides of the balls in table tennis, or a simple versus polyrhythmic condition in piano playing. And the movement noise level is almost the same in the two conditions we were comparing, for the predictable and unpredictable, and piano player, the rest simple and polyrhythmic condition. And so we were amazed by these preliminary findings, and so we decided to investigate more deeply the montage and the placements of FNIRS channels, which could be more prone to movement artifacts. So this led to this second paper in which we designed a block design experiment with some forced artifacts, which are very common in interpersonal communications, just like nodding up and down, sideways, speaking aloud, and raising the eyebrows. So we explored the impact of these artifacts with a montage covering the whole left hemisphere, with the cap fixed in Chen. Oops. Okay, sorry, I moved in my computer, I forgot to move here. And so we explored the cap strap in chin and chest. As a measure of impact, we considered the oxy and the oxyhemoglobin correlation and the coefficient of variation. And the COIN-D statistics was then used to quantify the effect size of these artifacts. And interestingly, the main condition that generated more artifacts were the eyebrows, the forced eyebrows conditions. And of course, we had the effects of the others, but they seem to be more manageable. And the second problem we wanted to address was the montage layout, where to place the electrodes. So since the numbers of the optodes is often limited for a whole head covering, and the placement for the channels is the channels grid is arbitrary at first. So in this paper, we present a toolbox to automatically create the optodes montage given a region of interest or an atlas such as Brodmann or AAL. This atlas contain clusters of voxels labeled as belonging to the same region, and based on Monte Carlo simulations, the toolbox provides the optimal locations of each source and detector, considering the desired sensitivity to this region of interest. In a more recent publication of our group, this more in the interfaces between education and neuroscience. Here, the mental rotation process in children around 8 years old was investigated using FNIRS. So the children participated in a brief assessment on basic geometry, of course, according to their grade. And particularly, FNIRS acquisition in children is very attractive because it's much more flexible than fMRI, without the noise of the scanner. The head is not so constrained, and it is not a claustrophobic environment. And moreover, the equipment is portable, so we can collect the data even at the children's school. So it is more, much better for them. So, and in this paper, we also do the simultaneous acquisition with eye tracking for pupillometric analysis using the glasses eye tracking. So this is an illustration of the paradigm. Periodic AB block was applied, alternating rest with a fixation cross and a mental rotation task. And this task, the figure and a rotation arrow was presented, and the children should imagine this rotation. And in the following, they should select the correct alternative representing the rotated image. So this is the pupillary response in percentage after the stimuli. And as expected, we found a statistically significant dilation during the imagectic rotation task, in line with the cognitive effort required to perform the task. Curiously, we found moderate around 0.4, but significant correlation between the activation coefficient, the betas of the GLM, and the pre-test geometry assessment. So in other words, the prefrontal, in this case, the dorsolateral prefrontal cortex activation in mental rotation and the geometric reasoning seems to be related in children. Great. In other study based on professional violinists' duos, we used hyperscanning and simultaneously measured the hemodynamic response of the two musicians. So the duo played a Bartók piece, which the main difficulty actually is not the execution, but it is the interaction between the violinists because of the changes in the tempo and other musicological features. And this is why this piece was chosen for this experiment. So while simultaneously acquiring FNIRS signals of the two participants, 4 blocks or conditions were considered. The violin 1 playing solo, violin 2 playing solo, the duo playing, and both violinists in rest. Just a question. I have 2 minutes? Ah, okay, no, I saw the 2 here. Okay. Thanks. When compared to the solo condition, we found a significant increase in the activation of the temporal parietal junction in violin 2 during the duo, but not in violin 1. The other regions, the motor and frontal, chosen as control regions, did not present this difference. So from a musicological perspective, considering that violin 1 is the leader and the second violin is the follower, the temporal parietal junction is often reported as involved in mentalizing process. So we believe this finding might be relevant to discussions in the field. Of course, there are a lot of limitations, but at least to raise some discussions, we thought that this would be interesting. So at the moment, we are still conducting other experiments involving piano duos as well. Okay, so although fNIRS experiments are less constrained than in fMRI, many of you may be asking, well, is this really real-life neuroscience? If statistical inferences is based on sampling from a population under a very specific condition, what is the possible generalization from this block or event-related designs, experiments, very controlled in the lab, to real-life situations? So, and actually, we have the honor to have the biggest name in naturalistic stimuli, Professor Hassan, here at the event, who inspired a lot of our works. So, all models are wrong, but some are useful. So this quote is attributed to the famous statistician George Box. No single model captures the full reality, and this is why they are models. Okay, so I am a fan of the Big Bang Theory, probably most of you as well. And in the first season, Leonard told this joke. A farmer has some chickens who don't lay eggs. The farmer calls a physicist to help. The physicist does some calculation and says, oh, I have the solution, but it only works for a spherical chicken in the vacuum. So, and I could not avoid laughing, because sometimes this is exactly what we scientists do. And thus, in the field of applied neuroscience, I think we inevitably have a trade-off between the control in perfect laboratorial conditions and the usefulness in real-life situations. Unfortunately, in real life is very different from the laboratory, and in my opinion, it is the experiment reproducibility and the results replicability that in the end really counts. Moreover, I work with children, and they really think that the non-naturalistic tasks are really boring. And so after some time, they just got tired and stopped collaborating. However, is it even possible to analyze fNIRS data of daily activity such as listening to a specific music piece or watching a video, which were not acquired in a block design experiment? So in this case, even the conventional general linear model analysis is not feasible. So let's start with a situation of a video presentation. And I think the situation is very familiar to Professor Hassan as well. In this study, from a group of 25 healthy children from 3 to years old watched a video. The name of the video is Inscapes, created by a group of Yale University. So this video was especially designed and produced to help the acquisition of fMRI resting state in children. The $1 million question is how to keep children still and quiet. And all parents probably know this, show them a video. So I use this trick in restaurants, churches, or in car rides as well. So in this case, our main concern was to develop an analytical method to explore these two questions. Can we use FNIRS to identify key moments in this video? And which brain regions are involved? So, well, I will not enter in detail, but these are the steps of the proposed method trying to answer these questions. And the intuitive idea behind the method is to identify the time frames, the video frames, when the spatial distribution of the hemodynamic signals are similar across subjects. So, in other words, these time points are the ones in which the brain activity is not spontaneous, but independent across subjects. They are similar across subjects. So here we use a bootstrap approach. Actually, it's a block bootstrap approach. And it has some similarities with interbrain correlation proposed by Professor Hassan, but this is in space, not time. And as the output of the analysis, we can identify which time points were more similar among the subjects, and we can also identify the regions which are contributing the similarities. Basically, we redo the analysis with and without each of these regions and see the impact. So, as a result, for this Inkscape and using a prefrontal montage, we rejected the null hypothesis that the brain activity spatial distribution is not similar across subjects. And after correcting for the hemodynamic delay, around 5 seconds, the main finding here is that all the time points in which the similarities across subjects were higher than Chen, this red, the line. These were video frames with 10 theme transitions. So that basically the theme of the video was changing. And that's probably, these are the frames of higher arousal due to novelty. And finally, the channel's importance regarding these hemodynamic similarities can be mapped. And the black bar here, which is the top 5% most contributing channels, is the dorsolateral prefrontal cortex. And still in education, we used FNIRS acquisition during a video lecture about astronomy at undergraduate level. The lecture lasted around 40 minutes, and we used the prefrontal montage while the participants watched the video. I don't know if you have already seen the Minority Report movie. I forgot the name of the main actor, but it's, yeah, who? Tom Cruise. Oh. So, yeah, this study was has some similarities with the main history of the movie. During the video lecture of astronomy, we a 10 quick quiz-like questions were asked to the participants. And these questions were strategically elaborated because they refer to some very specific content presented previously during the video. So the question were multiple alternatives with only one correct. So the question is, can we predict the right and wrong answer using solely the hemodynamic states during the specific content presentation. So, well, of course, first, we cannot disentangle the components of motivation, attention, and memory. But if the answer to this question is yes, we could predict the wrong answer even before they occur, just like in Minority Report. But I will not give further spoilers, okay? So in order to tackle this question, we used simultaneously the information of both oxy and deoxyhemoglobin and two machine learning classification methods, the random forests and elastic nets. We use these methods because, well, they are more proper when you have small data when compared to deep learning. And the input of these classifiers were the average of the pre-processed signal of the channels during the time window of interest, which are the video frames when the specific content of the question was presented. And the output were right or wrong. And the results, indeed, are, okay, they are not perfect, but they are better than chance, using a bootstrap method again. So the area under the curve, ROC curve, is above 65% for both random forest and elastic net. So this is not a striking result, but it's statistically better than chance. And in addition, by analyzing the variable's importance to the classification, we found that the medial portion of prefrontal cortex and right dorsolateral prefrontal cortex were important for both classifiers. And in this paper, in the Science of Learning, we illustrated how FNIRS hyperscanning could be useful to investigate the teacher-students interactions. And particularly, this is a very hot topic in learning theories because one of the main names in this field is Vygotsky, who highlights the importance of the social interactions for effective learning. And specifically, Vygotsky introduced the concept of the proximal zone in which the teacher mediates the potential learning of the student. So here we illustrated an experiment with a female teacher and a 3-year-old girl. We designed a board game in which the child has to toss 2 dice and sum up the outcomes and just do the number of steps in a trail, in a board. So the task of the teacher was to teach the girl on how to sum these 2 numbers and help and assist the child to execute this task. The cap montage on the bottom was designed to focus on the temporoparietal junction and bilateral prefrontal cortex. The layout was the same in both a teacher and child. The findings were in accordance to our hypothesis. The signals of the temporoparietal junction of the teacher here was correlated with the signals of the frontal of the child. As mentioned previously in the violin duo experiment, the temporoparietal junction is reported as involved in empathy and mentalizing processes, while the prefrontal cortex is involved in cognitive control. So in this case, our aim was, again, only to demonstrate that which kind of experiments could be conducted using FNIRS in the educational context and not to prove any theory. So generalization is not possible here, and of course there are many challenges. But we replicated these experiments in other 5 teacher-student pairs. And in this paper, using, again, machine learning approaches, we show how these machine learning methods could be used to analyze hyperscanning data. And we attempted to predict the student hemodynamic signals in each channel based on the hemodynamic states of the teacher using support vector regression. And another mathematical approach which can be useful in this situation is from the network analysis, which is graph theory. And in this case, each node of the graph was a brain region, a channel, but we considered the whole graph comprised of both brains, the student and the teacher. And community analysis in graphs is a frequent used approach to investigate a cluster of nodes. In this case, we have 2 straightforward communities, the subgraph of the teacher and subgraph of the student brain. And the question here is, how close are these 2 communities? Are they closer than chance? So, and by using time series bootstrap, we found the statistical significance in 4 from the 5 student-teacher pairs. And this is another hyperscanning study published this year. Oops, this one. And here we did simultaneous FNIRS in teacher and child again. But the child here was just a little bit older, around 8 years old. And the signal at different states were acquired for the purpose of comparisons, just like an introduction or doing independent activities. And well, here we were more interested in the interactive conditions. The task here was the teacher taught the children to code using unplugged, we call unplugged computing or unplugged coding approach. And it is based in a board game. Let me just show you how this works. So as an example here, we see this path of squares with an obstacle, the green here, square. A bot in orange in the top, and the target to be achieved in black. And in this, here, we see the commands the bot need to execute to go from starting to place, starting from a square to go to the target and achieve the target. So the game is interactive with coding and simulation and also with the teacher's assistance. And we use the same montage than before with optodes concentrated in dorsolateral prefrontal cortex and the temporal parietal junction. And when we used the graph theory, a graph theory metric named modularity, the whole brain graph was, again, composed of nodes, which are the FNIRS channels, and the links are the temporal correlations between oxy and the oxy hemoglobin signals, just like functional connectivity. The teacher and child brains were these subgraphs or modules, is again community analysis. And the modularity measure is a metric of how integrated are these subgraphs. So if the teacher and child signals are more independent from each other, the modularity is high. They are very distant distant from each other. So in a post-session video analysis of the experiments, the quality of interaction between the teacher and the child was scored by an educator who is an expert in this field, and was scored as low, medium, and high. So the main finding here was that this is a study based on around 30 pairs of teacher and child. And the main finding was that small modularity was associated with high quality of interaction. So, okay. So from education perspective and learning theories, these are very interesting findings. So, okay, so just some cautionary notes. Handling systemic artifacts requires the proper hardware for measuring short distance channels. And of course, head motion artifacts is perhaps the main challenge here. And if possible, use an accelerometer, place it in the head to help on this. And of course, I recommend you recording video all your acquisition for a posterior analysis. So to finish this presentation, I would like to highlight that this is a very interdisciplinary field, and which covers from all areas of knowledge, and this is really necessary. And remember that all models are wrong, but perhaps it is our job to discover how to make them useful to a purpose. There are numerous challenges, but innovation comes from the demand. By posing the challenges and the difficulties, we can also help to develop new methods. Okay, this is what I had. Thank you.
Okay, thank you very much for the interesting talk. I think we're a little bit over time, so maybe if you have pressing questions, we will have a discussion with all the speakers at the end, so maybe we save questions for then.
Of course.
Thank you so much. And